We will now continue our discussion of system of particles with spin 1/2. From the previous video, you will remember that we talked about the total magnetic moment, capital M, and its average value was the number of spins times the magnetic moment per spin average. Its dispersion was n times the dispersion of the magnetic moment per spin, and its standard deviation was square root n times the standard deviation of magnetic moment per spin. Now we call P the probability of having an up spin, and there is a corresponding moment. I'm going to assume that the charge sign is positive here, so it's going to be up spin corresponding to a positive moment, as opposed to the electrons where we have the opposite relationship. Okay, so the probability of having up spin is P, and there is a corresponding moment for the ith spin here. It is plus mu 0, and I call Q 1 minus P, that is the probability of having a down spin with the corresponding magnetic moment minus mu 0. Once again, I'm assuming that we have a positive charge here, so positive spin direction corresponds to positive moment. That's my assumption. Then I would like to calculate the average moment per spin. So this is going to be, by definition, it is the different values of moments I can have for one spin, and there are only two candidates, plus mu 0 or minus mu 0. So this is going to be the probability of having an up spin multiplied by its corresponding moment, the probability of having a down spin multiplied by its corresponding moment. So the answer will be P minus Q mu sub 0, and because Q is equal to 1 minus P, I can also write this as P minus 1 minus P times mu 0. So I would find that mu bar is equal to 2P minus 1 mu 0. So I can write it this way, or I can write it this way, P minus Q mu 0. They're the same thing. So now I know the average value, ensemble average, of the moment per spin. And just for checking, if P is equal to Q, the average moment should be 0, because I would have the same probability 1/2 for up spin and down spin, and this would happen with no external magnetic field. So that means the external magnetic field is 0. Okay, this is for this scenario, so I have checked this one here. Okay, so that's what this answer suggests. Now I need to find the dispersion of the magnetic moment per spin. So that's going to be the deviation from the average value, mu minus mu bar, square average. So this is going to be equal to, by definition, the probability of having an up moment, P, mu 0 minus mu bar squared, and then the probability of having a down moment, minus mu 0 minus mu bar squared. So this would be equal to P times mu 0 minus mu bar squared, and the minus sign has no meaning here because it's squared, q times mu 0 plus mu bar squared. Okay, so what I need to consider is what is mu 0 minus mu bar. Well, it is mu 0 minus 2p minus 1 mu 0, because mu bar was 2p minus 1 times mu 0. So that means in mu 0 parentheses I have here 1 minus 2p plus 1. So that is going to give me mu 0 times 2 minus 2p. That is 2 mu 0 times 1 minus p. 1 minus p is q. So I would find that mu 0 minus mu bar should be equal to 2 mu 0 q. And for mu 0 plus mu bar, I will have mu 0 plus 2p minus 1 mu 0. So it will give me at the end 2 mu 0 times p. So basically I can find from this the variance of the magnetic moment per spin is going to be equal to, so I'm substituting these two results, so this result will be substituted here and this result will be substituted here. So I will find this is going to be equal to p times 2 mu 0 q squared plus q times 2 mu 0 p squared. So the answer will be 4 mu 0 squared p q squared plus 4 mu 0 squared p squared q. So let's continue with this. I find the deviation, the variance or dispersion of magnetic moment per spin to be in 4 mu 0 squared p q parentheses. I have q plus p, but q plus p is 1. So therefore my answer for the variance of magnetic moment per spin is 4 mu 0 squared p q. Okay, and finally I can also find the standard deviation of the magnetic moment per spin. It's the square root, by definition it's the square root of the dispersion. So it's going to be equal to standard deviation of mu is 2 mu 0 square root p q. Okay, so before we talked about the total magnetic moment, and we found that as you can see in the reminder here, there's a relationship between mu bar and m bar. So now I can rewrite what m bar is. Now m bar is equal to n times mu bar, and for mu bar I have found p minus q mu 0, so it's going to be equal to n times p minus q mu 0. And for the variance of the total magnetic moment, delta m square bar, I found it's the variance of the magnetic moment per atom per spin multiplied by capital N, the number of spins. Therefore, I will find that the variance of the total magnetic moment should be equal to 4n pq mu 0 squared, and therefore the standard deviation of m, capital M, which is square root n times the standard deviation of mu, is 2 square root npq mu 0. So basically I have found the average moment, average total moment, the variance of the total moment, and the standard deviation of the total moment. So let me rewrite this one here. Two square root npq mu 0. And I can easily write the total moment. We can express the total moment in terms of mu 0 in units of mu 0. So remember, m is total moment number m multiplied by mu 0. So m is capital M divided by mu 0. It is also equal to the number of up spins minus the number of down spins, n minus n prime, which is also equal to n minus n, so 2n minus n. So I can remind you that for n number of up spins, what was the average value of n? The mean value of n is simply capital N times p. Now I can find the mean value of m using this relationship. Basically, if you take the mean value of this equation, you will find that mean value of m is mean value of capital M divided by mu 0. So the mean value of m should be n times p minus q, and the variance of the total moment number, delta m square bar, is going to be delta m square bar divided by mu 0 squared. So this is going to be 4 mpq and finally, for the standard deviation of m, which has the same dimension as standard deviation of capital M divided by mu 0, I will have standard deviation of capital M divided by mu 0. That will give me, for standard deviation of m, 2 square root npq. So this analysis shows me the possible, well, the most likely range of capital M and total moment number M values. So I will find that capital M values will be will most likely be in the range n times p minus q mu 0 plus or minus 2 square root npq mu 0. That's the meaning. Or I can find the total moment number m is in the range, most values are in the range n times p minus q plus or minus 2 square root npq. And this is quite clear why that's the case, because m is small m times mu 0. So basically this completes our analysis of the average values and standard deviation of magnetic moment number and total magnetic moment for the spin 1/2 particle system. Let's summarize what we did. There is something I didn't mention in too much detail here, that's n bar is equal to np. That's this equation here. And it's also possible to get all of these results going from statistical analysis of the number of upspins. I will go into a little bit more detail about this, where I will summarize all the results for the ideal spin system. So for now, let's take a look at what we did. In the previous video, we found the total magnetic moment average value is related to the total magnetic moment per spin average value with a factor of capital N, the number of spins in the system, and the variance is capital N times the variance of mu, and the standard deviation is square root n times the standard deviation of mu. Relative magnitude of fluctuations, standard deviation divided by the average, was scaling as 1 over square root n. That's what we have found out. Now I tried to calculate the values of average moment per spin and the standard deviation of the moment per spin. So I called P the probability of having upspin with a corresponding moment plus mu 0. So this cannot be an electron then, so it could be a proton, for example, a positive charged particle with a spin. And Q is equal to 1 minus P, the probability of having a downspin. And the average value of the moment per spin will be then the probability multiplied by all possible values, corresponding probabilities added together. P times mu 0, Q times minus mu 0 added together gives me mu bar, P minus Q, mu 0. And then I calculated the variance. Basically what I have here is a function of mu. What is the function of mu? It is mu minus mu bar squared. Mu bar is a number, so it's just a mu minus a constant squared. It's that function, I'm taking its average. So I multiply it with the probability P of having a value mu 0 minus mu bar squared, plus Q, probability of having a value minus mu 0, multiplied by minus mu 0 minus mu bar squared. And then I calculated what is mu 0 minus mu bar and what is mu 0 plus mu bar, which appears in this expression, and substituted the results here to find that the variance of the magnetic moment per spin is 4 mu 0 squared pq with a standard deviation square root of that answer, 2 mu 0 square root pq. Then we just substituted these results into the equations that have a capital M to find that the m bar is equal to n, capital N p minus q mu 0. The variance of the total moment is 4 npq mu 0 squared, and the standard deviation 2 square root npq mu 0. And this difference between capital M and total magnetic moment number m is that capital M is in units of mu 0, so it's m multiplied by mu 0. So once you have the answer for capital M here, you just divide it by m to get the answer for the total moment number m.